We now want to take a look at some topics that involve logarithms to other bases and exponents to other bases other than the natural logarithm and e to the x. Particularly, we want to start with a to the x. The logarithm was defined originally, the natural logarithm, in order to get at the continuity of the logarithm function and thus to have it defined for all values of x. Then the exponents. Now, at this point, we can define the function a to the x to be equals to exponent of x logarithm of a. That's to say, this is equal to e to the x natural logarithm of a. Now, the advantages of this is that if x is a rational number, then a to the x is equals to e to the x log a, which is equal to e to the natural logarithm of a to the x, which is equals to, see, this is exponent of logarithm, so exponent undoes what logarithm does because it's the inverse function, so this is equals to a to the x. Right? So for rational numbers, this justifies defining a to the x to be e to the x log a. Right? And now defining a to the x to be e to the x log a for all real numbers means that a to the x is going to agree with a to the x when x is rational. That's to say, e to the x log a agrees with a to the x when x is rational. Now, we want, of course, the derivative of a to the x. Derivative of a to the x. This is the derivative of e to the x log a. And now this is a composition. This is what? Exponent of x logarithm of a. So it's a composition of exponent with this. So the derivative is going to be equals to the derivative of exponent, which is exponent at x log a, times the derivative of x log a. Log a is a constant, and the derivative of x is 1. So the derivative of a to the x is equals to, this is a to the x again, times the natural logarithm of a. Okay, so now we've got, for any a greater than 0, we've got the function a to the x defined, and its derivative is going to be a to the x log a. We want to add to this at this point in time. We know the following, that the derivative of e to the x is e to the x, and now we know that the derivative of a to the x is a to the x log a. Right? We also know at this point in time, recall that the derivative of the logarithm of x, natural logarithm of x, is 1 over x. Right? So we have now these three things here. We can also get an antiderivative formula from this. That's to say, the antiderivative of a to the x dx is, well, a to the x would be a good guess. It's not right because the derivative of a to the x is a to the x log a. So if we divide by the natural logarithm of a, that's going to be right. So antiderivative now of the function a to the x, where a is any positive number, is going to be a to the x over log a. Once you have function a to the x defined, now it's natural, of course, now to complete the picture with the definition of log to the base a of x. Log to the base a of x is going to be the inverse function of a to the x. Right? Now this is for a greater than 0 and a not equal to 1. recall that the function a to the x now has got a graph that looks something like this. This is for a larger than 1. And of course for a less than 1 it looks like so. It's constant for a equal to 1. Huh? Okay, so the natural logarithm now is going to be the inverse of the function a to the x. Consequently, what? Its graph's going to look something like this. For example, for this a larger than 1. And we can compute its derivative using the fact that for the inverse function dx dy is equal to 1 over dy dx. So that the derivative of log to the base a of x here, what? Log to the base a of x equals y if and only if a to the y equals x. The derivative now is going to be 1 over the derivative of a to the y at y. So it's going to be 1 over a to the y log a. Right? That's to say, a to the y now is x, so this is going to be 1 over x log a. So that's an important formula. The derivative of log to the base a of x is 1 over x log a. Now, we could have gotten that in another fashion. I'm using the formula that's used for changing from one base to another. That's to say, we could write the log to the base a of x as the natural log of x divided by the natural log of a. Right? Now, actually doing this now is going to be a proof that this formula is correct here for all x and logarithm to the base a of x, because now the derivative of this is going to be, we know, is 1 over x log a. The derivative of this is 1 over x log a. Log a is a constant, so it multiplies the derivative of log x, and the derivative of log x is 1 over x. So this shows that this function right here has this for its derivative, and also that since it agrees, for example, with log to the base a of x at, let's say, 1, right? At 1, log to the base a of x is 0. This is 0 over log a. So it has these two functions here and this have the same derivative, and they agree at a point. So consequently, they must be the same function. There's a curiosity that we can mention here that perhaps doesn't have much of an application, but it indicates how to handle things, how to handle differentiation with respect to logarithms. The curiosity goes like this. Suppose we're looking at the logarithm, and we allow the base to vary. Suppose we have the logarithm to the base f of x of g of x. Now, I don't know of any applications for this, but this is about as bad as things could possibly be involving, the two things that are used with the logarithm. Suppose we wanted the derivative of this. Well, the way to take the derivative of this is to write this as the natural log of g of x divided by the natural log of f of x. Right? And in general here, when you're dealing with log to base a of x, any difficulties that arise can usually be avoided by changing to natural logarithms, right? Because here now what we get is, this is a quotient. The derivative is a little complicated, but here's what it is. It's the denominator log f of x times the derivative of the numerator, which is what? G prime of x over g of x minus the numerator, log g of x times the derivative of the denominator, f prime of x over f of x, all divided by the denominator squared, log f of x quantity squared. Okay, this is a curiosity. But what we have here that's not a curiosity is that the derivative of the logarithm is 1 over x log a. Perhaps something else to note here is that the antiderivative of natural log of x is, well, I'm just going to give it, you can check that it's right. It's x log x minus x. Plus any constant, of course. Right? And you can check easily that this is correct here. By differentiating the right-hand side, if we differentiate the right-hand side, we get that the derivative of this is a product, so it's the first times the derivative of the second, plus the second times the derivative of the first, now minus the derivative of x, which is 1, and so we get 1 minus 1 plus log x. So here's the antiderivative of log x. And one can then, of course, get the antiderivative of log to base a of x by writing it as log x over log a, and log a, of course, is a constant, so the antiderivative is going to be the antiderivative of log to base a of x is going to be the antiderivative of this, right, which is 1 over log a. Antiderivative of log x is x log x minus x. So there then is a formula for the antiderivative of log to the base a of x with respect to x. Okay, so now we have both the exponential function a to the x and the logarithm to the base a of x. Now, having the exponential function, we want to take a look once more at a function of the type that we're familiar with, namely x to the a. Now, if a is a rational number, then the derivative of this function, the derivative of x to the a, is ax to the a minus 1. Let's use this quite a bit. We want to see that now that we're this far along, that this formula actually holds whether a is a rational number or not. So we want to look at f of x equal x to the a, and compute f prime of x. Well, this is x to the a, the derivative of it, and now x to the a is e to the log of x to the a. That's to say it's e to the a log x. So we want the derivative of this. And the derivative of this is equals to, this is a composition, it's e to the a log x, so the derivative is going to be e to the a log x times the derivative of a log x. Derivative of a log x, a is a constant, derivative of log x is 1 over x. All right. Now this is equals to, e to the a log x was x to the a. So we have x to the a times 1 over x. Right. And now, using the rules for exponents, which can be checked, of course, for any two numbers here where the exponents make sense, we get that this is equals to x to the a times 1 over x. So it's x to the a minus 1 times a. So the derivative of x to the a is ax to the a minus 1. And this holds now for all numbers a, whether a is rational or not. So that, for example, the derivative of x to the pi power is pi x to the pi minus 1. Right? The derivative of x to the square root of 2 power is the square root of 2 times x to the square root of 2 minus 1. Okay. Likewise, we have from this the antiderivative formula, namely that the antiderivative of x to the a with respect to x is x to the a plus 1 over a plus 1 plus any constant. Right. This is for a not equal to minus 1. When a is equal to minus 1, of course, then we're looking at 1 over x, and the antiderivative of 1 over x is log x, natural logarithm of x. We can besides this get some additional formulas, namely that the derivative of f of x to the constant power a is, this is a composition, it's f of x with x to the a, so the derivative is a f of x to the a minus 1 times the derivative of f of x. And likewise, the antiderivative of f prime of x, f of x to the a dx, right, when a is any real number, right, is going to be equals to. Now this is a formula that's worth keeping in mind because sometimes you can recognize when you're dealing with antiderivatives that you've got something like this to deal with. The antiderivative is going to be f of x to the a plus 1 over a plus 1 plus any constant. And here, of course, this is for a not equal to minus 1. Right. If a is equal to minus 1, then the antiderivative of f prime of x, f of x to the minus 1, is going to be log absolute f of x. So we have now some formulas here that hold, in general, when a is a real number. These are just exactly the formulas that you'd expect, but now we've got them for sure. Well, we want to take a look again at the function e to the x, and in particular, we want to show that e to the x is equal to the limit as n approaches infinity of 1 plus x over n to the nth power. And this, we're also interested in this for a particular value here. E is then equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. We'll also get this as a consequence of this by putting x equal to 1 in here. Now this is not really an efficient way of computing the number e. If you try and do this with your calculator, you put, for example, a large number n in here, 1 plus 1 millionth to the millionth power. The amount of inaccuracy that's generated will probably not give you an accurate value of the number e. For computing the number e, one uses frequently the following formula, which I'm not going to prove here, but it's 1. Actually, so you can think of this as 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus, this continues on, 1 over n factorial and so forth here. This gives you the value of e, which is approximately, what, 2.718. Right? It gives you the value of e very rapidly to great number of decimal places. However, we want to take a look at this and see that this is what e to the x is. All right, for that purpose, we're going to start back with the fact that the derivative of the logarithm is 1 over x. We'll compute the derivative of the logarithm directly. That's to say, the derivative of the logarithm function is 1 over x. Now, if we were to compute this using the definition of the derivative, we would write that this is the limit as h approaches 0, logarithm of x plus h minus the logarithm of x divided by h. Now we can use the rules of logarithms here on this and write this now as the limit as h approaches 0 log of x plus h divided by x, and then we can take the 1 over h inside here. So 1 over h times this, and we can bring this to the 1 over h power. So this is this limit right here. And now, one thing we can do here, since the logarithm is a continuous function, you can bring the limit inside the logarithm. That's to say, interchange the logarithm and the limit. Write this as the logarithm of the limit as h approaches 0. And now we can simplify this a little bit inside here by writing this as 1 plus h over x to the 1 over h. Right. So we have now 1 over x is equal to this. Right. At this point now what we want to do is let 1 over h equal n. And then instead of looking at the limit as h approaches 0, look at the limit as n approaches infinity. So this now is going to be equal to the logarithm of the limit as n approaches infinity of 1 plus, now 1 over h is n, so that this is 1 over nx to the nth power. Logarithm of this. All right. And now we've got 1 over x is equal to this. Let's let t be equal to 1 over x. In which case we get t is equal to the logarithm of the limit as n approaches infinity, 1 plus t over n to the nth power. Right? So the logarithm of this quantity, right, you put a number t and you take the logarithm of this quantity, you get t back. So that means this must be e to the t. So this is the logarithm of e to the t, huh? You get t back when you take logarithm of this quantity. So consequently, this quantity right in here must be e to the t. And if we change the t now to an x, we find that e to the x is the limit as n approaches infinity, 1 plus x over n to the nth power. So that gives you this formula here for e to the x, and this formula here for e. So now I want to take a look at the subject matter of interest rates, or and we want to look at what's called continuous compounding eventually here. Let's look at simple interest rates. Suppose you put a quantity of money A in the bank. Right? Well then, if you want to know how much money you've got at any times t, and you start at time 0, A of 0 is going to be equal to A. If you receive interest on this money at the end of every year, then at the end of the first year, you're going to have A times 1 plus I. That's to say, you have the quantity A, plus you'll also have A times I added to it. So A of 1 year here is going to be equal to A, the quantity A times 1 plus I. If the amount of money is left in the bank for a second year here now A at the end of 2 years is going to be this quantity multiplied by 1 plus I, or A times 1 plus I squared. Right? Where I here, of course, is the interest rate. In general here, at the end of n years, or at the end of a time t where t is in years, you're going to have A is 1 plus I to the t power. This is t in years. Okay. Now, of course, what happened here is that this is compounding your interest annually, and interest is frequently compounded more often than annually. As to say, if you wanted instead to look at interest compounded biannually, so this is annually, right? If you wanted a biannual interest compounding, right, that's to say, it would be compounded twice a year, then A of 0 in this case is going to again be the amount A that's put in the bank, and A of a half is going to be A times 1 plus, you take the interest rate and divide it by 2, huh? A of 1 will be A times 1 plus I over 2 squared. And in general, A at any time t, where t is in half years, is going to be equals to A of A times 1 plus I over 2 to the 2t power. Right. So this is biannual. Right. Daily interest. Right. A of t is going to be equals to A times 1 plus I. Divide I into 365 parts and apply it 365 times t. Right? Where now t is in days. Well, t is in years. Right? But you can use any quantity of 1/365th of t will work here. Right? And this tells you then what the amount is at the end of times t. Monthly, it would be A 1 plus I over 12 to the 12th t power. Another question is, what would happen if we wanted to do this continuously, every second, every part of a second? What we want to do is we want to take the limit, define A of t to be equal to the limit as n approaches infinity, A times 1 plus I over n to the nt power. Divide the interest in n parts, apply it to A, right, and let n approach infinity here. This is also t in years, but allowing t to be multiples of a half. Huh? Okay, so A of t, if we went continuous interest, A of t should be the limit as n approaches infinity, A times 1 plus I over n to the nt power. All right, what is this? Well, the A can come out of the limit. That's the additional amount that's put in here. And now we want the limit as n approaches infinity, 1 plus I over n to the, now I'm going to change this here. I'm going to write to the n over I, and then to the times I to t. Right? Now what I want to do is I want to put this in parentheses here. And actually what I want to do is put the whole thing in parentheses, because I'm raising this to a power I to t as a continuous function, so the limit can be brought inside here. Now we look at the A, limit is n approaches infinity, 1 plus I over n to the ni power. And now if we think of a number n, right, this then becomes a limit as n approaches infinity, 1 plus 1 over n to the nth power, and this, of course, all to the I to t power, so that this is equals to, all right, as on the previous session here, this quantity here is e, so that this is a e to the I t. So for continuous compounding, a of t is given by ae to the I to t, where I is the interest rate. For example, 0.05 would be 5% interest. That's compounding continuously for small interest rates like 5% does not give you a quantity that's much larger than, let's say, even compounding annually or daily. Right? At the end of the year, with 5% interest on $1, one would not receive much more than $1.06. In fact, one would receive less than $1.06. Okay, now I want to take a look at a concept known as exponential growth. And interest compounded continuously is an example of that. Recall that we have a at any times t is the initial amount times e to the I to t power. And this is an example of exponential growth. I here, in particular, is some quantity greater than 0. Exponential growth in general consists of the situation where you have got a function f of x given by a e to the k x, right? And this arises whenever you've got the following situation. F prime of x is proportionate to f of x. If you look at a e to the kx, you find that f prime of x is a times derivative of e to the kx, which is e to the kx times k. So that f prime of x is a constant times f of x. Now, what's the interpretation of this? Well, whenever f prime of x is a constant multiple of f of x, then f is growing proportionate to the amount of f that there is. Some examples of this, here we have interest rates, right? Examples of exponential growth are population growth. Right? For example, if you've got a collection of bacteria, the bacteria tends to increase in numbers proportionate to the amount of them that there are there. Right? You then get something that graphically looks like exponential function as a function of time. That's to say, looks like this, where this is a of 0, or f of 0, right? And f of t is a e to the k to t, where k is greater than 0. Right? You can also have a phenomenon which is called exponential decay, and it's very similar here. If f of t is a e to the k to t with k less than 0, then what you have is something that looks like this. Here's a, which is a of 0, or f of 0, and as time goes on, the quantity involved decays. Right? Population growth is an example of exponential growth. Right? Radioactive decay. is an example of exponential decay. Right? That's to say, you've got a radioactive substance. It has what's called a half-life, and whatever amount there is here is at time A, it decreases exponentially, and so that as t approaches infinity, the amount decreases to 0. And there's also a quantity here which is called a half-life. Right? And that's the time when there is half as much as there was at time 0. Okay. Any function that satisfies this equation and is continuous is going to have, well, it's going to have to be continuous if it's differentiable. But any function that satisfies this, f, the derivative is proportionate to the value of the function, is going to have for its solution f of x is a e to the kx. Right? Moreover, if you note two values of f, you know f at some point x1, and you also know f at some point x2, then this is going to give you f. You can determine a and k if you note two values of f. So that, and frequently, the two values that are known are f of 0 and perhaps f at some other value, perhaps f at the half-life, let's say, if you're talking about radioactive decay. For example, if we knew that f of 0 was equal to 3 and f of 2 was equal to 4, then we can use that fact to find out what a and k must be in this equation here. For example, f of 0 equal to 3 means that a is 3, because when you put 0 in here, you get e to the 0, and f of 0 is what? 3 is a e to the 0, right, or a. So we now know a. Knowing a now, we've got that f of t is 3 e to the kt. But now we also know that the value at 2 is 4. F of 2 is 4. So this is equal to 4 is 3e to the 2k. If we divide both sides of this by 3, we get 4 divided by 3 is equal to e to the 2k. If we now take the logarithm of both sides of this, we're going to get the logarithm of 4/3 is 2k, so that k is equal to the logarithm of 4/3 divided by 2, and we have k here. We also have a here. A is 3, and so we know what the function is. F of x is 3e to this quantity k x. Right? If you know some value other than 0 for the function f, things are a little bit more complicated. We'll take a look at that next. Okay, we're going to take now a look at additional examples of exponential growth. In particular here, if we've got f prime of x is equal to k, f of x, then this gives rise to the fact that f of x is equal to a e to the kx for appropriate values of a and k. Right? Now, if you know a particular two values of f at two particular values, you can then find a and k. Let's look at a more complicated situation here where you don't know, let's say f of 0. Well, let's suppose we know that f of 2 is equal to 5 and f of 3 is equal to 7. Right? If this is the case, want to find out what f is. And we can do this as follows. We can write down what we know, namely that 5 is equal to AE to the k times 2, AE to the k x, and 7 is equal to AE to the k times 3. Right? Now if we take these two equations here, we can, if we divide one by the other here, we will get rid of the quantity a, so that we have 5 over 7 is equal to e to the 2k divided by e to the 3k. Right? That's to say this is e to the minus k. Right? And now we're taking the logarithm of both sides here. We get that logarithm of 5/7 is equals to minus k, so that k is equals to minus the logarithm of 5/7. That's to say it's the logarithm of 7/5. Do the rules for logarithms here, huh? So now we know k. And now once we know k, we can put k back in here and find out what a must be. That's to say a is equals to 5 divided by e to the 2k. E to the 2 times log 7/5. Right? And frequently here you can simplify this at this point, because what e to the 2 log 7/5 is going to be 2 log 7/5 is going to be log of 7/5 squared, and so this is going to be equal to 5 over 7/5 squared, which of course again could be simplified. What do we get? We get 125 over 49. Huh? So now we know a and we know k. From knowing these two values, knowing two specific values of the function f, the quantities a and k can be determined. Let's look it up. An example that represents perhaps a practical case. All right. Let's suppose we want to look at radioactive decay. Right. And let's suppose that we consequently want to know f of t. We know that it's equal to a e to the kth t. And let's suppose that there are 5 units of the substance here at time 0. So 5 is f of 0. And let's further suppose that this substance has a half-life of let's say 14 years. F of 14 is 2.5. We now wish to know, given this bit of information here, what's f of t? Well, since f of 0 was 5, we get that f of t is 5 e to the kth t. And now, since we know that f of 14 is 2.5, we get that 5 e to the k times 14 is 2.5. Right. 14 is the half-life here. And from this we can determine what k is. So we get 2.5 over 5, which is a half, is equal to e to the k times 14. So taking the logarithm of both sides here, we're going to get that this is k times 14, and so that 1/14th log of a half is k. That's to say k is equals to, bring the 14 inside the logarithm here, it's the logarithm of 1/2 to the 1/14th. So that we now write that f of t is equals to 5 e to the log a half to the 14th power t. And here we can write e to the log of a half to the 14th as a half to the 14th. And then this is to the t power, huh? So we can bring the t inside the logarithm here and write this as f of t is a half to the 14th t power. And then it's clear here for this expression of f of t that when t is 14, you have got, I should have a 5 here also, you've got a half of what you had previously. When t is equal to 14, the f of t is 5 times a half. When t is 28, the f of t is 5 times a half squared, or a quarter of what the original about 5 was. Okay, let's look at another here. Let's suppose that the population at times t increases exponentially, so that this is a e decay to t, and that the population, let's say, in 1970, which we'll take as times 0, of the United States was 2 billion, and the population, let's say, in 1990, which we'll take in years as times 20, is 2.5 billion. Then what we want is to find p of t, which will predict the population at each time t. Well, p of 0 is 2, so we know that p of t is equal to 2 e to the k to t. Right? P of 20 is 2.5. Right? So this is equal to 2 e to the 20k. E to the k times 20, huh? E to the 20k. Okay, so now we can divide both sides of this by 2 and take the logarithm, so that we get 2.5 over 2 is e to the 20k. Take the logarithm here, we get that this is equal to 20k, so the k is 1/20th of this. We now have k, right? And consequently, we've got p of t from here. We get k, and consequently, we know what p of t is, which will predict the population at any time t. That's one further thing here. Interest rates increase exponentially when they're compounded continuously. A of t is equal to a e to the I to t, where I is the interest rate. Now there's a curious thing that happens here, and it goes like this. Suppose we ask the question, how long does it take at a given interest rate for a person's money to double? So what do we want to know here? We want to know what's a of t. We want to solve for t when this is 2a. By what times t is a of t equal to 2a? Well, we get 2 equals e to the I to t. And taking the logarithm of both sides, we get logarithm of 2 is equal to I to t. Well, the logarithm of 2 is about 0.70. It's actually between 0.69 and 0.70. And this gives rise to what's sometimes called the rule of 70. That's to say, if you want to know how long it takes for money to double at a given interest rate, divide the interest rate into 70, and that will tell you how long it takes. So that, for example, at 5% interest, money will double, compounded continuously every 14 years. At 10%, it will take 7 years to double. Right? Conversely, if you want to know how much interest you need to make to double your money in a particular period of time, you can find the interest by dividing t into 70. This is called the rule of 70, and it's based on the fact that the logarithm of 2 is about 0.70. So, exponential growth, some examples here, one involving radioactive decay, and the other one involving population growth. We want to look now at some functions which are called hyperbolic trigonometric functions. They're called hyperbolic because they're based on a hyperbola rather than the circle which the original trig functions are. And these functions are defined in terms of exponents. And so consequently, anything that you can do with them, you can really do without them. That's to say, you can do just using the exponential functions. And we'll look also at their inverses, which turn out to be defined in terms of logarithms, understandably. And again, anything that you can do with the inverse functions, you can do without them. We're going to look at, first of all, a hyperbolic cosine function, written C-O-S-H of x, and pronounced sometimes cosh of x. This is e to the x plus e to the minus x over 2. So it's the average of e to the x and e to the minus x, and its graph looks like this. And here's e to the x, and here's e to the minus x. Then the average of the two is going to look like so. So here's e to the minus x, and this is the hyperbolic cosine of x right here. Now, this turns out to be a somewhat important function in that it's the shape that a rope has when it hangs, if the rope has got constant weight per unit length. Now, some people think that perhaps this ought to be a parabola, but actually that's not the case. The parabola is the shape that something should have if it's going to support, let's say, a bridge that's got constant weight going across. Right? So this is hyperbolic cosine function. Hyperbolic sine function is e to the x minus e to the minus x over 2. And if this here is e to the x, and if we now draw minus e to the minus x, it's going to look like this. Here's e to the minus x, and the negative of it's going to look like this. So this is minus e to the minus x. Then the hyperbolic sine function is the average of these two, and so consequently it looks like this. It's sometimes pronounced sinh of x. All right. Now for the ordinary sine and cosine function, you have cosine squared of x plus sine squared of x is equal to 1. For the hyperbolic sine and cosine function, what you have is that hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. This reflects the fact that the sine and cosine are based on the unit circle, whose equation is x squared plus y squared equals 1. You can think of the hyperbolic sine and cosine as based on a hyperbola, x squared minus y squared is equal to 1. And so these functions, for example, parameterize this type of a curve. Okay, to see that this is the case, let's just compute it. Hyperbolic cosine squared is e to the x plus e to the minus x over 2, quantity squared, minus the hyperbolic sine squared. That's e to the x minus e to the minus x over 2, quantity squared. Squaring here, we're going to get a quarter, and then we're going to have e to the 2x plus e to the minus 2x, that's the other squared term. And for the middle term, we're going to have 2 times e to the x times e to the minus x. So this is going to be e to the x times e to the minus x is e to the 0 or 1. So we're going to get plus 2 for the middle term. And then this is minus a quarter. Again, here we get e to the x, e to the 2x, and e to the minus 2x. And for the middle term here, we get a minus 2. Right? So altogether here, what this is it's a quarter times 2. These terms, a quarter e to the 2x minus a quarter e to the 2x, that cancels out. Quarter e to the minus 2x minus a quarter e to the minus 2x cancels out. And so we end up with this 2 times a quarter plus 2 times a quarter, or 1. All right. So there's a relationship between the hyperbolic cosine and the hyperbolic sine. The second relationship is as follows. The derivative of the hyperbolic cosine. If we take the derivative of the hyperbolic cosine, what do we get? We get e to the x minus e to the minus x over 2. That's the hyperbolic sine. And likewise, the derivative of the hyperbolic sine, if we take the derivative of the hyperbolic sine, we get e to the x minus e to the minus x times minus 1. So that's e to the x plus e to the minus x over 2, and that's the hyperbolic cosine. So the derivative of the hyperbolic sine is hyperbolic cosine, just like for the trig functions. The derivative of the hyperbolic cosine is the hyperbolic sine. It's very easy to remember. And in fact, the fact that the formulas for these functions work out to be so nice is one of the reasons why they're used. So the hyperbolic sine and the hyperbolic cosine. We want to look now at the other hyperbolic trig functions. The hyperbolic cosine, first of all, is e to the x plus e to the minus x over 2. And the hyperbolic sine is e to the x minus e to the minus x over 2. And we have that the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. Now the other hyperbolic functions are defined naturally in terms of the sine and the cosine. That's to say, the hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine. And the hyperbolic secant is 1 over the hyperbolic cosine. Right? And now, dividing this equation here, this identity, dividing it by the hyperbolic cosine squared gives us 1 minus sine squared over cosine squared is going to be tangent hyperbolic squared. And 1 over hyperbolic cosine is going to be secant hyperbolic squared. Right? So that there's an identity here similar to the trigonometric identity. Of course, the trigonometric identity is 1 plus tangent squared is secant squared. Here, there's also such an identity. All right? The hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, and the hyperbolic cosecant is 1 over the hyperbolic sine. Right? And now dividing this through by hyperbolic sine squared, we're going to get hyperbolic cotangent squared here, right, minus 1 is going to be equals to 1 over hyperbolic sine squared, which is hyperbolic cosecant squared. Right? So here's a similar relationship for the hyperbolic cotangent and cosecant. Now, the derivative of these functions are somewhat interesting. They're pretty much along the lines that you might expect. The derivative of the hyperbolic tangent. This is hyperbolic sine over hyperbolic cosine. So the derivative is going to be the denominator, hyperbolic cosine, times the derivative of the numerator, which is hyperbolic cosine again, so that's hyperbolic cosine squared, minus the numerator, hyperbolic sine, times the derivative of the denominator, derivative of hyperbolic cosine is hyperbolic sine, so this is hyperbolic sine again, over hyperbolic cosine squared. Now, hyperbolic cosine squared minus hyperbolic sine squared is 1, so this is 1 over hyperbolic cosine squared, so the derivative of the hyperbolic tangent is the hyperbolic secant squared. So it's exactly similar to the situation with the original trig functions here. Right? The derivative of the hyperbolic secant hyperbolic secant is 1 over the cosine, so the derivative is going to be the denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, so it's going to be minus hyperbolic sine over the denominator squared over hyperbolic cosine squared. And we have the hyperbolic tangent derivative hyperbolic secant is going to have for its derivative minus hyperbolic sine over hyperbolic cosine squared. It's easier to write this, though, as minus sine over cosine, which is going to be hyperbolic tangent. And we have a 1 over cosine left over, which is hyperbolic secant. So the similarity here is obvious to the derivative of the secant. Huh? The derivative here is minus the tangent times the secant. All right. Similar situation here with the hyperbolic cotangent. The derivative. Well, this is a quotient, so the derivative is the denominator, hyperbolic sine, times the derivative of the numerator, which is hyperbolic sine again, minus the numerator, hyperbolic cosine, times the derivative of the denominator, which is hyperbolic cosine again here, over the denominator squared, which is hyperbolic sine. Okay, so that here we have then the derivative of the hyperbolic cotangent. Well, hyperbolic sine squared minus cosine squared is a minus 1. So this is going to be equal to minus 1. So we have minus 1 over hyperbolic sine squared. 1 over hyperbolic sine squared is hyperbolic cosecant squared. So the derivative of the hyperbolic cotangent is the hyperbolic cosecant squared. Let's to finish the picture here. The hyperbolic cosecant for its derivative. All right, the hyperbolic cosecant is 1 over the sine, so the derivative of the denominator times the derivative of the numerator. The derivative of the numerator is 0, minus the numerator times the derivative of the denominator. That's going to be minus the hyperbolic cosine over the denominator squared, hyperbolic sine squared. Right? And now this is usually written in this fashion, minus cosine over sine, hyperbolic, is cotangent. And 1 over sine is cosecant, hyperbolic. So the derivative of the hyperbolic cosecant is minus hyperbolic cosecant cotangent. So again, the similarity. So these are the other hyperbolic trig functions and their derivatives. Now, the thing to note is that all these functions can be defined in terms of e to the x and e to the minus x, and so that, while they do have applications, frequently what you can use them for, you can do without using them. Right, we now want to take a look at the inverses of the hyperbolic trig functions. These also have some application. However, again, what you can do with them, you can do without them, as you will see. Recall that hyperbolic cosine of x is equal to e to the x plus e to the minus x over 2. And the hyperbolic sine is the same, except that here there's a minus sign. Right? The hyperbolic cosine function has a graph that looks like this. And the hyperbolic sine function has a graph that looks like this. This is the hyperbolic sine, hyperbolic cosine. Now, so you'd expect that the hyperbolic sine will have a true inverse. Its derivative of the hyperbolic cosine is positive, so the hyperbolic sine is increasing. Hyperbolic cosine, however, is going to have two parts to its inverse, the left and the right-hand side here, so that for each y here, we're going to want a particular x here, and there's another alternative x also. So let's let y equal to e to the x plus e to the minus x over 2. Then we've got e to the x plus e to the minus x is 2y. We want to solve this now for x to find the inverse function. Right? To do that, let's multiply through here by e to the x. So we get e to the 2x plus 1 minus 2y e to the x is equal to 0. Now, if we write u equal to e to the x, then this looks like u squared minus 2yu plus 1 equals 0. This is u squared, and this is u. Right? So that we get that u is equals to minus b here, the quadratic formula. This is a quadratic equation, except that, of course, we've got a 2y here, so this is going to be 4y plus or minus the square root of 4y squared minus 4 times 1 over 2. And now this was u is e to the x here. So we can get x here by taking the logarithm. And we could simplify this side by dividing 2 into here. Y plus or minus the square root of, here taking the 4 outside of the square root here, we get y squared minus 1. Right? So that this is hyperbolic cosine inverse of y. Given a y, it tells you what x should be. Right? Obviously, hyperbolic cosine inverse of x would be the log of x plus or minus the square root of x squared minus 1. And the plus and the minus should give you the two parts. Now, if we were dealing with the hyperbolic sine, then we would have a minus sign here. Right? And that would produce a minus sign here. All right? Which would produce a minus sign here. And consequently a minus sign here. And so the only difference that we would get here would be when we took b squared minus 4ac, we would have a plus 4 instead of a minus 4 here. So this would produce a plus sign here. So the hyperbolic sine inverse of y is the log y plus or minus the square root of y squared plus 1. Right? And now here the plus or minus is chosen so that this quantity inside the logarithm is positive. So that, for example, if y is greater than 0, then y squared plus 1 is larger than y, so you can't choose the minus sign for it. If y, on the other hand, is less than 0, then y squared plus 1 again is larger than y, and so you can't choose the minus sign. So consequently, the correct inverse for the hyperbolic sine function is this logarithm right here. Now, it's clear that anything that you can do with hyperbolic cosine and hyperbolic sine, you can also do with logarithms. I'm going to look at one more inverse hyperbolic trig function because it's used somewhat, and that's the hyperbolic tangent inverse. The hyperbolic tangent of x is the sine over the cosine, so it's going to be e to the x minus e to the minus x divided by e to the x plus e to the minus x. Recall the hyperbolic sine is e to the x minus e to the minus x over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. So this is the hyperbolic tangent. It's defined for all x. And the graph, as x approaches infinity, this goes to 0 and this goes to 0. And the numerator and denominator here approach e to the x over e to the x and get close to 1. Right, so if this is 1, 1 is an asymptote here. And likewise, as x approaches minus infinity, minus 1 is an asymptote. What? As x approaches minus infinity, e to the x approaches 0, e to the x approaches 0 here. And what you're left with is a minus 1 over here. This gets close to minus 1. You can see that by dividing through if you wish. And so the graph, at any rate, of the hyperbolic tangent of x looks like this. The derivative of it is the hyperbolic secant squared, which is positive, and so the hyperbolic tangent is increasing. You can convince yourself of that. And the range is a minus 1 to 1. All right, so the hyperbolic tangent inverse of x will have domain from minus 1 to 1. And range, of course, minus infinity to infinity. All right, and so it's going to look something like this, what you'd get if you flip this about the line y equals x. Right, so if we let this equal y, then we want to solve for x. And so we have e to the x times y plus e to the minus x times y equals e to the x minus e to the minus x. Right? Let's multiply this through by e to the minus by e to the x so that we get e to the 2x times y plus y is equal to e to the 2x minus 1. Right. Let's collect the e to the 2x terms to this side here so that we have, on this side over here, we've got minus 1 minus y equals, on this side over here, we've got e to the 2x times y minus 1. So we get e to the 2x is equals to 1 plus y over 1 minus y, dividing both sides by y minus 1 and correcting this with multiplying numerator and denominator by minus 1. So that we get, taking the logarithm of both sides, we get the logarithm of 1 plus y over 1 minus y is equal to 2x, so that x is equal to 1/2 the logarithm of 1 plus y over 1 minus y. So this is equal to the tangent hyperbolic inverse of y, or the hyperbolic tangent inverse of x. Is what you get if you put x in here. And that's sometimes written as 1/2 log 1 plus x minus log 1 minus x. And now the reason why this tends to have some uses is because the derivative of the hyperbolic tangent inverse is going to be 1/2. The derivative of log 1 plus x is 1 over 1 plus x times the derivative of 1 plus x, which is 1, minus the derivative of log of 1 minus x, which is 1 over 1 minus x times the derivative of 1 minus x, which is minus 1. So we get this. And then putting this over a common denominator here, we have 1 minus x squared, and we get 1 minus x in the numerator, and we get 1 plus x, which is going to be equal to plus 2. And now we've got a half here to contend with, so we get that the derivative of the hyperbolic tangent inverse is 1 over 1 minus x squared. Right? However, while some people prefer to use this fact, I want to note one more time here, namely that this is also a hyperbolic tangent inverse, and we will see when we work with antiderivatives that you can get this as the antiderivative just as easily as this one right here. However, the derivative of the hyperbolic tangent inverse is 1 over 1 minus x squared, so consequently sometimes this is used as an anti-differentiation formula, namely the antiderivative of 1 over 1 minus x squared is hyperbolic tangent inverse. Hyperbolic tangent inverse of x. Hyperbolic. We want to look now at the trigonometric functions and their inverses. Beginning with the tangent inverse, which is probably the most important of them. Now the trigonometric functions are not one-to-one, so a choice always has to be made as to what the inverse function is going to look like. So that, for example, tangent of x looks like this, between minus pi over 2 and pi over 2. It increases here from minus infinity to infinity. But then it repeats. Well, this is a natural choice here, right here, for the tangent inverse function. So we will end up with a tangent inverse function that looks something like this. Right? The domain is the tangent inverse of x, or arctangent of x, sometimes called. Think of it as the angle whose tangent is x. The domain is going to be minus infinity to infinity. And the range, since the domain of the tangent function here is minus pi over 2 to pi over 2, is going to be minus pi over 2 to pi over 2, excluding the two endpoints. It's worthwhile noting while we're right here that pi over 2 is an asymptote. Y equals pi over 2 is an asymptote for arctangent, as is y equals minus pi over 2. And the limit as x approaches infinity of the arctangent is consequently going to be pi over 2. The limit as it approaches minus infinity is going to be minus pi over 2. Okay. We can get the derivative of the tangent inverse function as follows. Tangent of arctangent of x gives you x back. Take arctangent of x, take the tangent of it, you get x back. And so if we differentiate both sides here, we're going to get derivative of the tangent is secant squared. So we want that at arctangent of x times the derivative of arctangent of x is 1. Right. So that we get that the derivative of arctangent is equals to 1 over secant squared of arctangent of x. But there's really a better way to write this. If we let theta be the angle whose tangent is x, so if theta is the angle whose tangent of x, and we draw out a triangle here, then this side here can be represented by x, and this side by 1. And consequently, the third side of this right triangle here is going to be square root 1 plus x squared. So the secant, well, the cosine of this of theta is going to be 1 over the square root 1 plus x squared. That's going to be 1 over the square root of 1 plus x squared. The secant is going to be the square root of 1 plus x squared. And the secant squared is going to be 1 plus x squared. So this secant squared of the angle whose tangent is x is 1 plus x squared. It's the square root of 1 plus x squared squared. So that the derivative of the arctangent is the square root of 1, is 1 over 1 plus x squared. Right? And this makes for an important anti-differentiation property. That's to say, when you have something like 1 over 1 plus x squared, to anti-differentiate, the antiderivative of this with respect to x is arctangent of x. In fact, sometimes people write this as the antiderivative of 1 over x squared plus a squared is equals to 1 over a arctangent of x over a. Right? This type of formula can be checked. At any rate, here's the derivative of the arctangent function, and consequently this gives rise to an important anti-differentiation formula. One that's perhaps a little bit surprising. Here you've got something which is really a rational function, and its antiderivative is the arctangent. So there's the arctangent and its derivative. All right, we next want to take a look at the arc sine of x. And again, here a choice has to be made. Sine of x looks like this. And now this repeats. And the function is definitely not 1 to 1. And generally what's done here is from minus pi to pi, the function is 1 to 1. And this section of it right here is chosen for the inverse function. And so consequently the inverse sine, or arc sine, and here, keep in mind that this minus 1 here on the inverse sign indicates the inverse, and you never read sine to the minus 1 of x here as anything but the inverse sign. If you wanted 1 over sine of x, that's either cosecant or it's sine of x to the minus 1 power. At any rate, here we've chosen minus pi to pi for the domain here, and so that's going to end up as the range of the sine inverse function. The graph is what you get if you reflect this through the line y equals x. It looks like this. The domain is minus 1 to 1, including both endpoints. And the range is minus pi to pi, again including the endpoints. Right. And we're going to want the derivative of this function. It's a derivative that shows up sometimes in applications. So we take the sine of arc sine of x, and this is x. And differentiating both sides, you get the derivative of the sine is the cosine. The cosine, that arc sine of x, times the derivative of arc sine of x, the derivative of it is equal to the derivative of the right-hand side here, which is 1. So we get that the derivative of the arc side is 1 over cosine of arc side of x. And again, this is that in a convenient form. We want the cosine of the angle whose side is x. So if we let theta be the angle whose sine is x, arc sine of x, right, then this is going to be theta, and x, if we put x here and 1 here, then that will represent theta. And the other side of this triangle here then is going to be the square root of 1 minus x squared. So if the cosine of the angle whose sine is x, the cosine of theta is going to be the square root of 1 minus x squared, and so this is going to be 1 over the square root of 1 minus x squared. It's the derivative of the arc sine of x. Right? And this, along with the arctangent, are worth remembering, and likewise we're going to find that the arc secant is worth remembering. However, the others are redundant. The antiderivative also here, consequently, of 1 over 1 minus x squared square root with respect to x is going to be arc sine of x plus any constant. So here's the derivative formula and the antiderivative formula involving the arc sine. Derivative of arc sine is 1 over square root 1 minus x squared. Right, we wish now to look at the third inverse trig function, the inverse of the secant. And for this purpose here, since the secant is 1 over the cosine, let's draw a cosine x here. Right, so that this is 0, the secant, this is cosine x. And the secant consequently looks like this. All right, and likewise over here, and over here, and so forth. So this is secant x. Right. We need to make some sort of a choice as to what we're going to use for the inverse of this function. And a choice that's frequently used here is this. This part right here, this is perhaps the choice that's most frequently used, and this part right here. Right. And then the resulting graph of the secant inverse will look like this. If we rotate this about the line y equals x, we get, this starts here at 1, and increases up here to pi over 2. And then it comes back in the other side here, so to speak, and goes up to 1. So it's not defined as pi over 2. And comes back up here, like so, at minus 1. So that the domain, this is the secant inverse, or arc secant, the domain is going to be minus infinity to minus 1, excluding the minus 1, along with 1 to infinity. And the range is going to be 0 to pi over 2, along with pi over 2 to pi. It's not it doesn't have pi in its range because the secant's not, pi doesn't have pi over 2 in its range because the secant's not defined at pi over 2. All right, the derivative of this is sometimes used, or sometimes occurs. So we want the derivative of the secant inverse, and for that purpose, again, let's look at the secant of arcsecant of x. And this, of course, gives you x back, right? Providing you take x over here in the domain of the arcsecant. So this is equal to x, and so the derivative is going to be the derivative of the secant, which is secant times tangent at arcsecant times the derivative of the arcsecant. And this is going to be equal to 1, the derivative of x. So we get that the derivative of the arcsecant is 1 over secant of arcsecant of x is going to be x again. Right? Actually, we have to be a little bit careful here with this, but I'll say something about it in a minute. So we have x times the tangent of the arcsecant. It's the derivative of the arcsecant. Now, this is not in its most convenient form. We want the tangent of the angle whose secant is x. So for that purpose, let's draw a triangle here. Let's let theta equal secant inverse of x. So here's theta. It's the angle whose secant is x. The secant's 1 over the cosine. So it's going to be, if we put x up here, we put 1 down here, then this will represent theta, the angle whose secant is x. And consequently, this third side over here is going to be the square root of x squared minus 1. Right? And the tangent of the angle whose secant x is going to be the square root of x squared minus 1. So 1 over x, square root x squared minus 1, is the derivative of the arcsecant. Right? And even if x is negative here, right? Even if x is negative, the way the arcsecant function is defined, the choice of arcsecant function, makes it so that the arcsecant is increasing. So for this choice of arcsecant function, the derivative is always going to be positive. And so frequently what one does is writes 1 over absolute x, square root x squared minus 1, to make sure that this is the correct antiderivative of the arcsecant. And then, of course, one has the antiderivative formula, 1 over absolute x, square root x squared minus 1 dx. The antiderivative of this is arcsecant of x plus any constant. So here's the arcsecant and its derivative. That doesn't show up quite as often as the arctangent does, or the arcsine. Arctangent being the one that shows up the most often. Arcsecant of x. Now we want to take a look at the other inverses now and see why they don't end up being used particularly. Let's first of all look at cosine of x. All right. Well, the graph of cosine of x looks like this. Right. And the place that's generally chosen for the inverse of this when it is used is between 0 to pi, where the function is 1 to 1. And so the cosine inverse function, or arc cosine of x, has a graph that looks like this. It starts out here at 1 and goes up here like so. So its domain is from minus 1 to 1, and its range is from 0 to pi, including the pi. Right? However, if you think about it here, you look at a triangle. If theta is the angle whose cosine is x, so here's x to 1, and theta is equals to arc cosine of x, then phi, the other angle in the triangle, is going to be the arc sine of x. That's to say, what we're going to find here is that the arc cosine of x plus the arc sine of x add up to 90 degrees, or pi over 2. Or, if you like, the arc cosine of x is equal to pi over 2 minus the arc sine of x. And so consequently, anything that you can do with the arc cosine, you can do with the arc sine by just writing arc cosine as pi over 2 minus arc sine. It's worse than that, though, because, of course, the derivative of the arc cosine is going to be the derivative of pi over 2, which is 0, minus, is going to be the derivative minus the derivative of the arc sine, which is 1 over square root 1 minus x squared. So that the arc cosine doesn't give you anything new in terms of antiderivative that you couldn't get also using arc sine. And so consequently, the arc sine is the one that's used rather than the arc cosine. The same situation is going to hold true for the cotangent. Cotangent of x looks like this and repeats. And the natural place to use for the inverse function is between 0 and pi, so that we end up over here with cotangent inverse looking like this. When we revolve this, it's decreasing and goes down here to 0 like so. Here's cotangent inverse of x, or arc cotangent of x. It goes from pi down to 0 for its range. Right. Now, similarly here, if we draw a triangle here, and if theta is the angle whose cotangent is x, then what have we got? Let's say this is x and this is 1. Right? So if theta is arc cotangent of x, then the other angle in this triangle, phi, will be the angle whose tangent is x. And again, what we have here is that arc cotangent x is pi over 2 minus arc tangent x. So you can use the pi over 2 minus arc tangent x instead of arc cotangent of x. And moreover, the derivative of this is going to be the derivative of this, which is the derivative of pi over 2 is 0, minus 1 over 1 plus x squared. So you don't get anything new in terms of antiderivatives either. You can take the antiderivative of 1 over 1 plus x squared using the arc tangent. So there's nothing new there particularly either. Right. Finally, the cosecant. Right. To draw the cosecant, our best bet is to draw the sine, which looks like this. And here's the cosecant, consequently. It's the reciprocal of the sine. And when the cosecant inverse is used, the most common way to develop it is to use this part here of the cosecant and this part right here. So that consequently, the cosecant function, so cosecant inverse function is going to be what you get if you flip this about the line y equals x. That's to say, it's going to come in here like, it's going to come up here like this, and it's going to come down here like so. And so this would be cosecant inverse of x, or arc cosecant of x. Okay, again here, if you draw a triangle, you find that if theta is equal to the arc cosecant of x, then phi is the arc secant of x. For example, if theta is the arc cosecant of x, the angle whose cosecant is x, that's going to be x to 1. Then phi up here is going to be the angle whose secant is x. Oops. Angle whose cosecant is x is going to be x to 1, and phi is going to be the angle whose, the angle whose cosecant, that's 1 over the sine. So this is going to be x to 1. X to 1. Theta now is the angle whose cosecant is x. All right? Now, that's the angle whose sine is x. X to 1. Right? Theta now is the angle whose cosecant is x, and phi will be the angle whose secant is x. X to 1. All right? And so again, what we're going to get is that arc cosecant x is pi over 2 minus arc secant x. And so the derivative of arc cosecant x is going to be the negative of the derivative of arc secant x, which is minus 1, let's say minus 1 over absolute x times the square root x squared minus 1. Right? And it doesn't give anything new in terms of antiderivatives, and nor in terms of derivatives or functions, because you can always write the arc cosecant this way here if it's desired to have something like it. So there's nothing really new with the arc cosine, arc cotangent, or arc cosecant. And it's the functions that don't have cos in front of them, the tangent, the sine, and the secant, which are used for the calculus. All right, with these new functions now, in particular, the logarithm and exponent, of course, from before, but the sine inverse, the tangent inverse, and the secant inverse, you want to make sure that you can take derivatives of these functions and combinations of these functions with other functions. So, for example, suppose we've got the logarithm of sine inverse of x. We want its derivative. What is the composition of this logarithm of sine inverse of x? The derivative is going to be 1 over sine inverse of x times the derivative of sine inverse of x, which is 1 over the square root 1 minus x squared. Right? How about another one? Tangent inverse of e to the x. Suppose we want its derivative. Right? The derivative is, this is the composition, is tangent inverse of this function. So the derivative is going to be the tangent inverse 1 over 1 plus x squared at e to the x times the derivative of e to the x. So there's the derivative of tangent inverse of e to the x. Take the form for the tangent inverse function and you put the composition, the g from the composition in there. Right. Let's try secant inverse of 3x. Suppose we want its derivative. Right. Derivative of the secant inverse is 1 over absolute x square root x squared minus 1. We want that at 3x, and times the derivative of 3x, which is 3. Right. How about arctangent of x cubed? This is arctangent of x to the third power, so the derivative is going to be 3 arctangent of x squared times the derivative of arctangent, which is 1 over 1 plus x squared. And any combination that you make up here, it involves the inverse sine, inverse secant, inverse tangent. You ought to be able to differentiate. Try one more here. Arcsine of x divided by arctangent of x. So if you want the derivative of this, what's the quotient? The derivative is the denominator. And the derivative of the numerator, 1 over square root 1 minus x squared, minus the numerator, arcsine of x, as the derivative of the denominator. Derivative of arctangent is 1 over 1 plus x squared, all over the denominator squared. Okay, so any combination with these new functions, arcsine, arctangent, and arcsecant, to be able to differentiate. And differentiating is quite a bit different story, and it's considerably more difficult. But here you've got the formulas for the derivatives, and so all the possible combinations of these functions with others should be able to differentiate.